The 8051 timer. A timer is a hardware counter that counts at a predetermined interval. The basic 8051 has two timers. However, some derivatives of the 8051 may have three timers. The timer can be configured to run as 8-bit, 13-bit or 16-bit timer. Let's focus on discussion on the 16-bit timer. The 16-bit timer has 16 binary bits. The timer counts at a predetermined interval. It can count from 0 to all ones. After counting to a maximum of all ones, the timer goes back to all 0. This condition is called an overflow. The timer continues to run after an overflow. Instead of representing the 16-bit timer in binary, it is more convenient to use hex number. 16 bits binary can be represented by 4 hex digits. In terms of hex number, the timer can count up to a maximum of FFFF. The timer then goes back to 0 and continues counting from 0. The timer to be discussed here will be based on the Silicon Lab C8051F226 microcontroller. Let's take a closer look at timer 0. This is the logic diagram of timer 0. This is the 16-bit counter of the timer. This counter is made up of two registers, TH0 and TL0. TH0 and TL0 are 8-bit registers classified under the special function registers. These registers are used to control and monitor the timer operation. They are all classified under the special function registers. These are two external signals. This signal is controlled by this bit in the TCON register. This bit is called a timer 0 run control bit. This signal is controlled by this bit in the T-mode register. This bit is called a timer 0 gate control bit. This double throw switch is controlled by this bit in the CK-con register. This bit is called a timer 0 select. This double throw switch is controlled by this bit in the T-mode register. This bit is called the counter timer 0 select bit. Let's take a closer look at the T-mode register. These 4 bits are related to the control of timer 0. These 4 are for timer 1. These 2 bits are called the timer 0 mode select bits. The timer can be configured as 8-bit, 13-bit or 16-bit. Timer 0 is configured to run in 16-bit when these bits are set to 0 and 1. This bit is called a timer 0 overflow flag. The system clock provides the timing for the circuit. Changing the gate 0 bit will change the gate 0 signal and in turn affect the operation of the circuit. The timer 0 clock select bit selects the clock that feeds the timer. It can be the system clock or the system clock divides by 12. The counter timer 0 select bit selects either the system clock or an external signal called T0 to feed the timer. For our discussion, we will stick to using the system clock. The timer 0 run control bit activates the running of the 16-bit counter in the timer. Timer can be stopped by putting this bit to 0. The counter value can be set, for example, to all 0. Let's set it to FFF0. Let's start the timer. Observe the timer 0 overflow flag as the timer overflows. The timer has overflow and the timer 0 overflow flag is set to 1. After overflow, the timer continues to run as long as the timer 0 run control bit is 1. The timer 0 overflow flag can be cleared to 0 by software. Let's stop the timer by clearing the timer 0 run control bit. Let's look at the source of the system clock. This logic diagram shows how the system clock is derived. The system clock can be selected from two sources. The selection is made by controlling a bit in the internal oscillator control register. Upon a system reset, the internal clock is selected. This is the external oscillator control register. The bits in the external oscillator control registers are used to configure the external oscillator circuit. When the external oscillator circuit is stable, the crystal oscillator valid flag is set to 1. This is to indicate to the user that the external oscillator is ready for use. User can then control the bit in the internal oscillator control register to select the clock from the external oscillator circuit. Assuming a crystal of 11.0592 MHz is used, the system clock will therefore be 11.0592 MHz. Let's come back to the timer 0 logic circuit. The system clock is 11.0592 MHz. The clock feeding the timer is 11.0592 divided by 12, which is 0.9216 MHz. This gives rise to a clock period of 1.085 microsecond. Let's take a closer look at the timer counting. The timer is fed with a clock with frequency 0.9216 MHz, or a clock with a period of 1.085 microsecond. Every count takes 1.085 microsecond. Let's set our timer to FFFA. How much time does it take the timer to reach overflow? It took the timer 6.51 microseconds to reach overflow. Let's set the timer to FFFA. Run the timer. When the timer overflows, the timer 0 overflow flag is set. And this took 6.51 microseconds. The timer continues to run after the timer overflows.